So far, we've used tables and graphs to understand our golf ball's flight. A graph is an amazing tool for seeing the big picture. We can see that it opens downward and we can see roughly where the vertex is. But graphs have a hidden weakness: precision. Imagine a tree is blocking our shot. It is exactly 40 feet tall, and our ball reaches it at exactly 1.5 seconds into its flight. Will the ball clear the tree? Let's look at the graph. If we go to 1.5 seconds and follow it up to the curve, the line crosses right at the 40-foot mark. But is it at 39.8 feet? 40.2 feet? 40.5 feet? On a graph, a few inches is just the width of a pencil mark or a single pixel on a screen. If you are playing in a major tournament, it looks like it might clear it. Isn't good enough. You can't eyeball precision. To get a guaranteed, exact answer, we need to go beyond the picture. We need the actual mathematical rule driving the ball. Behind every parabola is an equation. For our golf ball, this is the exact rule. Height equals -6 times time squared plus 36 times time. Look closely at this equation. Notice how our variable, t for time, is being squared. In our first lesson, we learned that a parabola has a change in its change that bends it into a curve. In algebra, that squared exponent is the signature of that bend. The moment you add a squared variable, it bends the math into a parabola. Now, let's use this rule to solve our problem with absolute certainty. Does our ball clear the 40-foot tree at 1.5 seconds? Instead of squinting at a graph, we just plug 1.5 in for t. First, 1.5 squared is 2.25. Multiply that by -6 and we get -13.5. Next, 36 times 1.5 is 54. Finally, add those together. -13.5 plus 54 equals 40.5. At exactly 1.5 seconds, our ball is exactly 40.5 feet in the air. It clears the tree by just 6 inches. A graph couldn't show us a 6-inch difference, but algebra gives us the exact precision we needed. This brings us to a major mathematical shortcut. You don't even need to plot a graph to know if something is a quadratic function. You just look at the math. If the highest power driving the rule is a square, what we call x squared, you are looking at a quadratic. So, before we move on to lesson 4, I have a quick challenge for you. On screen, there are 4 different mathematical relationships. 2 of these are already written out in algebra. The other 2 are real-world rules. For C and D, think about what the actual math rule would have to look like if you wrote it out with y and x. Based on what we've learned about steady changes versus changing changes, and looking for that squared signature, which of these are quadratic functions and which are not? Pause the video, write down your guesses, and we will reveal the answers and their exact rules at the very beginning of the next lesson. See you then.